Okay, hello everyone. It's my pleasure to finish the day today with the topic of quantum rewinding. And in this talk, I will do three things. First, I will tell you what rewinding actually is, in case you're not familiar with it in the classical world. Then I will talk about what the problem is with rewinding when we go to the classical setting. And then I will show to you two different kinds of quantum rewinding, namely what I call oblivious rewinding and extraction rewinding. I'm not sure there are any really established names for the two kinds. And then if we have time, I'm also happy to, I'm happy to answer questions all the time, and especially in the end, if you have any bigger questions and so on. Okay, so let me start with the question, what is rewinding? And for this, instead of trying to give any general definitions, I will show you a little example that I will use to illustrate the various concepts. But many of the things I will show to you can be applied in many more contexts than just this one setting. So the example that I have is that of graph isomorphism proofs. This is a kind of zero-knowledge proof that is probably not very practically useful because graph isomorphism is not a particular hard problem. It's just hard enough to be annoying. But it's a nice example because of its structural simplicity and so on. So let's say we have this prover here who wants to prove to the verifier that two graphs G and H that are known to both are isomorphic. So the prover knows an isomorphism between G and H, but the verifier, the black cat, knows this isomorphism. So and we could of course just send the isomorphism, but we want to do it in a way that the verifier after the proof is convinced of the existence of the isomorphism, but will not know what the isomorphism is. So how can we do that? The protocol works as follows. So first, the prover takes the graph G, so one of the two graphs that are isomorphic, and permutes it and sends the result of permuting verifier. Now, this does not reveal anything about the isomorphism because the isomorphism hasn't been even used. Then the verifier sends a challenge, in this case of 1 bit. So it says whether it picks the graph G or whether it picks the graph H. So it chooses one of the two graphs. And now what the task of the prover is to send a graph isomorphism between J and G or between J and H. So it has produced this permuted and now shown that the graph is isomorphic to G or that it's isomorphic to H, depending on what the prover wanted. And now intuitively, this still doesn't lead the isomorphism between G and H because it just leads an isomorphism between some random graph and G or some random graph and H. But it's also convincing because in order to succeed with a high probability here, the prover needs to know isomorphisms to G and to H from J, from the same graph J, and those can only exist if G and H are indeed isomorphic. So that's the basic intuition of this protocol. So let's look at this in slightly more detail and see how one would prove the security of this protocol with the specific attention to rewinding happens in it. So let's first look at the zero-knowledge. So for the zero-knowledge property, what we need to do is so for the property that the verifier doesn't learn anything about the isomorphism, we need to show the following. We need to show that for any malicious verifier, it is possible to create a simulated interaction that is what the verifier would actually talking to the prover. And if the simulated interaction is done without using the witness, indeed think about the witness because it's just seen something that does not use the witness. So obviously the verifier will not learn the witness. So how do we do this? Well, what we do, very roughly, I don't want to go into the details that are not relevant for this talk, is when trying to simulate an interaction with the verifier, and remember, we don't have the witness, so the isomorphism, so we can't just run the prover. What we do is, before we send this first message, the so-called commitment, which was the shuffled graph, we just guess what the verifier will send in the second step. This is just one bit, so we have a good chance of being right. And this protocol has the particular property that if we already know what we will be sent in the second stage, then we prepare the first message in a way that we will be able to correctly. Because the response in the end needs to be an isomorphism between the graph G or H, depending what the verifier wanted, and the one that we have sent here. So we just sent the one, we just sent here a graph J that is a reshuffling of the graph that we actually want to later show that we are isomorphic to. So we guessed the challenge. If we have guessed the challenge correctly, one can see easily that it is possible to run this interaction, and the verifier will output exactly as it would do in a real world interaction, conditioned on the fact that we guessed right. If we guess the challenge wrong, we have to abort this attempt of simulating. So what we have in this picture so far is a way of simulating the interaction, but with the possibility of aborting, and we only know that conditioned on not aborting, we have produced the right output. So what do we do if we want to have the right output all the time? And this is where rewinding comes in. So when we simulate this interaction, we get the challenge, and then we know whether we guessed right or wrong. And if we guessed wrong, we just go back to step 1 or 0 and start again. And this is rewinding. I mean, this is one example of rewinding. So we do an execution, and then we undo one or several steps and continue from an earlier state. This variant of rewinding I call Oblivious Rewinding, because we just forget everything we did. We just go to an earlier state and run it again. We do not need to remember, for example, what the wrong challenge was or the wrong commitment or something. We just go back, forget everything, do it again. This we repeat until we are successful. This is the basic proof strategy for showing that this protocol is zero knowledge in the classical setting. The second property, so we have seen now one variant of rewinding, Oblivious Rewinding. Second property we may want to look at is the proof of knowledge property. So we want now to show that you cannot cheat in this proof if you are the prover. So we want to show that if the prover knows the isomorphism, the prover cannot win, cannot produce a convincing proof with probability better than 1/2. And 1/2 is probability, but you could repeat it sequentially to get it lower. So in this protocol, all we care is to show that you cannot win with probability better than 1/2. And how do we prove that? Well, imagine you have a prover that succeeds in this interaction here with high probability. Think of it maybe with probability 1 for simplicity, but in the concrete proof, you would have to be more precise with the probabilities involved. So let's say the prover wins with probability 1. So we run this prover internally. So it produces the commitment or the shuffled graph. We pick one of the two graphs, and we get a response. As we said, since it's zero knowledge, this does not tell us anything about the witness. But what we do now is we just rewind to this step. So we go back to the state of the prover when we had just gotten the commitment, and we send the other challenge to the other graph. And since we have a prover that succeeds with high probability, we are likely to get a second response that is also a correct response to the second check, but for the same commitment message. So in our concrete setting, it would mean that we have one graph J from the commitment message and from the two responses, an isomorphism from J to G and an isomorphism from J to H, and those together gives us an isomorphism from G to H. So by running this thing here, we get isomorphism between G and H if we have a prover that has a probability higher than 1/2 of succeeding. The property that we have used here is called special soundness, which says that if you have two responses for different challenges but the same commitment, you can efficiently compute witness from that. So that's the general property when we're talking about so-called sigma protocols, which are protocols that have basically that structure like the graph isomorphism protocol. Mm-hmm.
Very basic question about isomorphism. Is it equally easy to go from J to H and from H to J?
Yeah, so the question is basically whether you can efficiently invert an isomorphism. Yes, because the graph isomorphisms are actually just but once you have it, you can because it's just a pair of vertex here, vertex there. So working with these isomorphisms, it works all very smoothly. And that's indeed an important question, because if we want to get an isomorphism from G to J, we actually compose the inverse of this arrow with this arrow. So that's probably why you asked. Okay, so this is an example of a different kind of rewinding, because we are not kind of going back and trying again, but instead we are going back and we're getting additional information, but we also remember something from the first execution. So that I call extraction rewinding, because I don't have a better name. If you know a better name, please let me know. Now, these two examples are quite well known when people talk about rewinding. Zero knowledge and rewinding, they very much go together. But it turns out that sometimes rewinding is even used in moments where people don't notice that rewinding is used. So I will give you an example where many people who do crypto will say, yeah, it's obvious, and no, there is no rewinding involved here. But and do the actual, you notice, oh yeah, there is rewinding. I still claim it's obvious, but with a completely different argument. So the example is the following. Consider a hash function and a horse race. And we are in the following situation. We have a player who wants to bet on a horse, in this case, Spicy Spirit. And because the player does not want to reveal before the race what horse they are betting on, what they do is basically to build a commitment scheme. And for concreteness, I designed a commitment scheme here. It's hash of name of the horse, comma, sufficiently long randomness. So this is a pretty standard way of making a commitment if you have a hash function. The hiding subtle, if this is just a collision resistant hash function, then you would need to do more, but we only care about the binding of the commitment here. So then collision resistant hash function and this thing should give us a binding commitment. So the player sends this to the bookie. Now the horse race happens, Spicy Spirit wins. The player sends the randomness, the bookie can check that hash of Spicy Spirit and that randomness is indeed the message from earlier, and the bookie sends back the money. Here, a bag of Bitcoins or something. Okay, that's the honest case. What if we try to cheat? So let's say I claim the cheating player can actually do the following. The player can, instead of sending hash of Spicy Spirit, send some fake hash. And then Walloping Waldo wins the race and not Spicy Spirit. And now the player just comes up with some value R, that hash of Wallop, R is the hash value from earlier, and the bookie sends the money over. So you ask, could this happen? And you'd think that if H is collision resistant, this will not happen because you can only do that. I mean, if you want to win with all horses, you can only do that if you can find the pre-images of H, both containing Walloping Waldo, and both containing Spicy Spirit. So you need to have two pre-images for the same value H. And actually the same kind of reasoning is used kind of in a lot of moments when you use commitments. And if you make a coin toss from commitment, use also the same reasoning. And it's a direct application of the resistance of the hash. But actually, if you do the proof, which I will sketch here, you will see, no, it's actually extraction rewinding that we do here, and there's no way to do it differently. So the actual proof, or proof sketch for this would be, if we have a player that successfully cheats often, or like can send a hash H, so that for a lot with high probability, it will be able to answer to this horse question, then we just simulate an interaction. So we let the player produce a hash value H. Then we tell it horse 1 won, like let's say Walloping Waldo. Then we get the response, so that horse 1 response 1 is the hash from earlier. Then we rewind the player, tell it horse 2. It will also give us a response because it wants money. And now we have a hash of horse 2 and response 2, which also is the hash value from earlier, and we have a contradiction. But you cannot do this without rewinding. I mean, I don't have a proof that you cannot do it without rewinding, but the fact that we will later have problems with the quantum setting is a strong indication that something like this needs to happen. So, and as you see, I was even lazy. I just copied the picture from earlier and changed the words. It's the same kind of rewinding. It's extraction rewinding again. In a different setting, same way. Of course, you could have more complicated cases of extraction rewinding. For example, you could go several times, or maybe you could go up to a different degree and something like this. In this talk, I will just focus on the simplest case, the ideas, yeah, leave anything complicated to you because I like simple things. Okay, so to recap what we have seen so far, we have seen two kinds of rewinding, but I would like to stress this does not mean these are the only things that we could do with rewinding. They're kind of two different use, whereby rewinding, I mean anything that go back to an earlier state in some hypothetical interaction and then continue. So we have seen these two like very important use cases, oblivious rewinding and extraction rewinding. And in oblivious rewinding, the general situation that we want to solve is we are given some simulator S that, or generically some algorithm S, returns the right result, the result we want, or it fails. And we want to rerun it to get the right result all the time. So that's oblivious rewinding. We needed it for the ZK property. And then we have extraction rewinding, or extracting rewinding, how it used to be called right now. There we have some adversary A that gets a certain challenge, returns some valid response S, and this adversary we run with some challenge, then we go back, run with another challenge, get two valid responses, and that's the kind of rewinding we need for the proof of knowledge, but also for the commitments when we use it in the horse race. And there are probably many other situations where it crops up in hidden ways. Okay. Are there any questions about the general rewinding? So I'm closing the classical thing now. Yes, you could say so. I mean, where you might branch for different reasons. In one case, you branch like right thing, wrong thing. In the other case, you branch because you need both execution, but you can see it. I mean, I don't know whether you could formally see it as some branching because I'm not sure what a branching. But but intuitively, I think it is some kind of branching. Yeah, but together with the random probabilism and so on, I'm not sure you can really narrow this down that it's correct formally, but I think intuition, I would say it's probably right. Yeah.
The Oblivious Rewinding, is it still the verifier that you're rewinding?
In the Oblivious Rewinding, I mean, in the example that I gave you, we were rewinding the prover. No, we were rewinding the verifier because we tried to convince the verifier and we needed to guess what will convince the verifier. Well, we are actually rewinding a simulator that contains the verifier. Yeah, but if we are talking about the general technique, we are basically rewinding something that until it gives us what we want. So you can abstract these things a bit and just see it as some general. I have some algorithm that does something I want, and I want it to succeed more often by running more than once.
It was
Yeah. Okay. Okay, so let's see what the problem is. So remember we had, so here I drew again the two pictures from the Oblivious Rewinding and the quantum rewinding and the extraction rewinding. And in both cases, what we have is that we go back to an earlier state. And I just said, go back to an earlier state without actually saying what this exactly means. And in the classical setting, there are no subtleties involved there. Well, there are subtleties involved there, but no really big that anyone cares about, except me, myself, maybe. But in the quantum setting, it becomes really subtle. So the problem is, if I want to an earlier state, what I need to know is I need to know that earlier state. So actually implicit in this picture is here, before we make the commitment, we copy the state into some auxiliary memory. Then we run this, and then we move back the auxiliary, the side memory, put it back into the main memory, and have restored the state. So we have this of duplicating the current state, copying it in order to restore it later. You cannot do that. It's like when you run a virtual machine. When you run a virtual machine, you have these snapshots where you can go back, but you can only go back to a snapshot if you made the snapshot. You cannot decide the next day, oh, I would like to go back to the snapshot from yesterday. So I didn't make it, but I still want to. It's the same here. You need to make the snapshot. And unfortunately, you cannot do that in the quantum setting. Because in the quantum setting, making snapshots means copying a state. This state could contain quantum information, and you cannot copy quantum information. So that's the problem. And let me address maybe something that you might find here, that what about this part here? I mean, we are rewinding to the very beginning. Why do I need, what quantum state do I need to copy? I mean, I just need to start from the beginning. And indeed, this picture may be a bit misleading in that respect or incomplete. But if you look at the exact definitions of zero knowledge, it will say something like, for every statement, for every witness, and for every auxiliary input given to the verifier, you can do the simulation. And this auxiliary input in the definition is usually quantum. Now you may again complain that, yeah, but then just don't put this quantum auxiliary state in the definition, but you actually need it there. What happens if you don't put it there is that if you want to repeat your protocol sequentially, then already the second execution of it has the state from the first execution. So if you try to get some composition theorems that you can repeat it sequentially, it will break down. And if you try to analyze the repeated protocol directly, then you actually end up doing like rewinding. Oh, I go only 3 steps back and not to the very beginning. So it may look at the first glance you can get around it, but whatever you try, you will notice there is some quantum state somewhere. So you really need to copy a quantum state to do these 2 kinds of rewinding here. So annoying situation, and actually one of the first places where quantum rewinding was mentioned in the literature was in Van der Graaf's PhD thesis, where it was basically as an argument that quantum MPC is probably not possible. So we have come far since then, 95 or something. Also, you may wonder, okay, we cannot do rewinding in the classical sense, but that's just a proof technique problem. Maybe most protocols are still secure, except we haven't figured out yet how to prove it. And in some cases, this is indeed correct, but we can even show that in some cases, the same protocol a protocol that would work classically with an assumption classically does not work quantumly under the corresponding quantum assumptions. So just to give you 2 examples of this, which relating to the things we had before, there exists a sigma protocol. So a sigma protocol is a protocol of this structure similar to the graph isomorphism that has special soundness. Special soundness meaning that given 2 interactions, you can compute the witness. More specifically, computational special soundness. So it means it is hard to find an example. It's hard to find 2 interactions from which this extraction algorithm that computes the witness would fail. So a subtlety here. So you have this special soundness computationally, which classically means with the rewinding we get that it's a proof. But quantumly it has special soundness against quantum polynomial time adversaries and not a proof of knowledge for quantum polynomial time adversaries. Similarly, we can construct still relative to some oracles or very strong non-standard assumptions, so we don't have any natural examples. You can construct a hash function that is collision resistant, but if you plug it into the horse race example I gave you, the player can win all the time. So the player cannot find collisions, but it can always open the hash value as whatever it wants. It can just not open the same hash value as 2 things that it wants. Because once it opens it as 1 value, it doesn't know, it forgets how to do that. That's a very quantum thing. For classically, you can't just forget how to open things to other values by doing it once. Quantum case, there is you create the hash together with some state, and this state is information how to open the hash value to whatever you want. But if you run this, but if you do that, you have lost the state. So subtle thing, and a very surprising kind of stuff. And actually, this links back to the talk we just had, because remember, Andres mentioned that the adversary method was used in some non-standard setting. That was exactly to prove those counterexamples. So yeah, so that's bad news. Fortunately, it wasn't too devastating because we found this bad news after we already had the good news. But it still means that we cannot hope to have the quantum rewinding work with the same amount of generality as the classical one. And just so that you know, it's like if you put here in, for example, perfect special soundness, or well, if we strengthen the assumptions, things work, but we need new assumptions. Okay, so now I've shown you why what rewinding is. I've told you why rewinding does not are in the quantum setting. So any questions about this, about rewinding in the quantum setting? horrible ones. So let me try to remember the oracles. I'm probably not going to get the details exactly. So there was one oracle. So basically it picks some set of values that you should know. Then it gives membership for that set, for a random set. So that's pretty harmless. It gives you a so it's actually a family of sets. So we have a lot of these random sets. We have membership for each of them. Then we have an oracle, which for every input gives me, I think, a pair of an index from that set family and an element from that set. So I can easily pick one of those sets and then a member, but I cannot pick two because next time I get it from another one. Otherwise, then I have an oracle that, so for every set, state that is the superposition of all the members of that set. There's an oracle that allows you to get copies of that state, I think. And then there's one oracle that unitary 1 minus projector onto that state. And that's all. Yeah, exactly. The same ones are the same oracles are you. Once you have these oracles, you can do all.
What is the kind of something like I would imagine it just a 2 to 1.
Sorry?
Like if you have a 2 to 1.
Yeah.
But the adversary would need to be able to choose where to collect.
Yeah.
So that's not
Exactly. Yeah. So you mean you make a superposition, like basically you have a superposition now of two pre-images, but now I tell you, I want the pre-image from those two pre-images that you have. Please give me the. I got the one that was not starting with 0. And then you have exactly probably 1/2, which is exactly the same as you would get classically by guessing what will be asked of me later. Yeah. So it's it's a bit wild. Okay, depending how much time it is, maybe I can tell you later a bit more how it's done, if you remember. But let me first go through with the talk as I have prepared it, and then we see. Because I think I'm pretty good in time, which means pretty bad at planning. So let me now tell you how things can actually be done. So let's start with the Oblivious Rewinding. So let's recall. So in the case of Oblivious Rewinding, what we are doing is we have a simulator that produces some desired input, well, some desired output state or output distribution of states, and it files with probability 1/2. But conditioned on not failing, it gives us exactly what we wanted, or something very close to it. In the example we had, it was exactly, but you, in more complex example, you might be happy to allow some error. And we want the simulator the desired output all the time, except for some negligible probability of failure. And we want the output not just like some valid output, we want it with the same distribution as this original failing simulator does. So how can we do that? So the idea is that we, instead of, so we cannot rewind. So instead of, in the classical sense of copying the state and restoring it. So the idea is to not even try to copy, but instead we want to uncompute. So we make some computation and then we want to go back and then say, okay, we just undo all the computation steps. So how do we do that? So this is something we couldn't have done in the classical setting, at least not in the way it's normally defined, because information is lost. your virtual machine loses the state from earlier. But also in a classical virtual machine or a classical algorithm can always be replaced by an algorithm that is reversible. And the same thing we can do in the setting. So the first step is that we take the simulator that fails or not and replace it by a unitary transformation that does the same thing. So today in the first talk, I think this was at least touched. I don't remember in what detail. So you can always, if you have any classical algorithm, you can always transform it into an algorithm that only performs unitary operations by just, in addition to the input, providing some auxiliary input, some state with auxiliary qubits that is initialized with state. And then the simulator runs, and gives us an output. This output will now also have some additional quantum bits that should be thrown away, but yeah, I should have written an extra wire, but it's not that important here. So we now are in the setting that we have a simulator that is completely unitary. And often in the beginning of the proof, it's just done by saying, without loss of generality, the simulator is unitary, but strictly speaking, this is a first transformation step. And sometimes you need to be careful with that. For example, if your simulator calls some classical oracles, then you need to also actually make them unitary and so on. And that may, so you should be aware that you did that, because then you cannot later rely on the fact that they are unitary, classical. Okay, so this is step one. And why did we do that? Because unitary operations can always be inverted. So now we have made our simulator into a invertible simulator, because we can just take the adjoint of the simulator, and this is the inverse operation of the simulator. So running the simulator and the adjoint cancels out. Running the adjoint and then the simulator also cancels out, but that is less useful for us. Yeah?
So if the original simulator is accessing a classical oracle,
yeah.
How do you construct this?
Well, you would construct the unitary, you would first transform the classical oracle into a quantum oracle.
But if you don't know the inner
if you cannot do that, well, you could say, we don't know what it looks like, but it is some transformation of the classical oracle into something unitary. I mean, you don't necessarily, I mean, you also don't know how S works because it contains the verifier. But so that may be enough, but it depends on the situation of the concrete proof you're in. It may also just mean that you're stuck. So it depends very much, it depends on the concrete situation, whether you have a big problem or something that is simple to fix.
So this implicitly, this technique of going from S to unity of S,
yeah, I mean, as it's written here, it just assumes that there is no oracle. But if you have an oracle, then you need to rethink this in the concrete situation, and it will mean that quantum oracles or not. Automatically happen because when you transform let's say you have an algorithm S that does only classical queries, that takes, like, let's say it queries it has a random oracle and it queries it at a random input. So now if you make the oracle, if you make S into a unitary, what you do is the following. Maybe I can draw this. No, whether there's some wiping. There's a wiping thingy. Tell me whether I frame of the camera, and I will try to draw.
That's perfect.
This is the start from here to here. Okay, and how low? This is my whiteboard. Good. If you do something like random, and then this thing goes into the oracle H. something like this. This would be the classical algorithm. So this goes into the classical Oracle H. That would be you take cat0. Maybe I should draw it bigger. Well, too late. You put it into a mask, get a equal. So that it feels classical. And now this thing here goes into the, oh, damn it. This is Hadamard H and this is Oracle. So you put it now into this Oracle, but you have never measured this. So this is actually a superposition query, even though it started as a classical one. And I don't know of any way to kind of say this is a harmless one because we started classically. Maybe there is, but I don't know it. Yeah. You mean this measuring here? Yeah, I mean, this one I haven't reached yet, but yeah. If you mean some, I mean, we have reached this part, and I've mentioned this one because it was written here, but I mean, I just say it's invertible. Step 2, I will come to in a moment if it's about step 2. And then you can if you want. So what we have done now is we have replaced our simulator, and well, we haven't gained anything yet really, because it still fails half of the time. So this output maybe contains a bit like I failed or I didn't fail or something like this. And now it can fail in superposition. That's the only thing that changed. So step 2 is now the interesting thing. So what we do is what we wanted to do in the Oblivious Rewinding is if the simulator fails, we go back to the beginning and restart. And this we now do not by restoring the state, but by undoing the computation. So we have here the simulator, it runs. Now we measure whether we succeeded. If we succeeded, it's fine. If we didn't succeed, we apply the inverse of the simulator, and we start again the whole thing until it succeeds. Now, you asked whether the measuring doesn't disturb things, and indeed it can disturb things. So when analyzing this, one needs to be careful to see whether this is a disturbance that is annoying or it's a disturbance that's not annoying. It turns out in this case, it's a bit annoying. We will see in a moment why, but fixably annoying. So at the first glance, this might be working. I mean, like as a idea, like we undo it, we try again until it works. So let's see whether that's the case. Let's see what happens in this loop. So we run the simulator, we measure whether we have success. Let's say we don't have success. So we apply S dagger, then we apply S, and then we measure again. Wait, we have applied S dagger and S in a row. They cancel out. So what we're doing actually is we run the simulator, we measure whether the final stated output was successful. If it wasn't, we measure again whether it's successful. And we are in an infinite loop of just staring at the stupid state and waiting for it to be successful while we don't do anything. So this really does not work. That was my first attempt. But fortunately, we can fix this. And now comes the part that is a bit non-intuitive, because what we do is before going back, we go to this auxiliary state and do something confusing to it. So first, what should, in an ideal world, what would the auxiliary state here be? Well, we start with cat0. So maybe it should be, ideally it would be cat0 again if we had gone back to the initial state. Well, what we could do is we could throw it away and put a cat0 there, but that doesn't work. What we do instead is we make a phase flip depending on whether it's cat0 or it's not. Well, if you read that, it may seem like very weird why you would do it, why would it, but it does. So this little disturbance means at least it means that this S-dagger flip S is not an entity anymore. And it's out that now this algorithm works. I don't want to go through the analysis why, also because it didn't prepare it. But if you remember from the first talk, the Grover algorithm, Gorjan had a picture on the board, on the slide that was something like there's a superposition between having found the good one and the bad one, and then you do a query and things go over here, and then you do this, and it goes. This, if you remember a picture like this, it turns out that's exactly what happens here. So this flip means that instead of going back to the bad case, you kind of flip it to you flip it somewhere else from which you have a chance on the next measurement to go where you want. So the analysis is kind of similar. Yeah. No, it can be many qubits. A bunch of times. So I mean, you have a success probability that it works on the first. I mean, you have the original success probability, and the first measurement will succeed with exactly the original success probability because you do the original thing. Each of the successive ones, I think if the original success probability was P, the other ones worked with P times 1 minus P or something like this, but independently. So then you can just compute the success probability after a certain number of rounds in some easy way. Yes. Then I guess we have then just proved that this does not happen. Because if that would happen, then we have seen that the simulators cancel out and that extraction doesn't work. And we have Vatros result that extraction does work. So under the assumptions of Vatros theory, we can conclude that the auxiliary state in the end still contains a zero.
So one thing to remember, I guess the auxiliary, like morally, the auxiliary state includes kind of randomness that we needed to sample freshly in the classic case.
No, it does. It does contain it here, right. Like, but we undo everything. Like if we wouldn't have this measurement of success, this 1-bit measurement, then the auxiliary state here would be 0.
But this randomness is independent of the input, right? The randomness in say
yeah.
protocol.
Yeah.
So in some sense, the measurement that samples it needs to act on the auxiliary, right? So I think that's the key movement.
Yeah. Yeah. Or you can also make the argument that you can bound the disturbance of the state that measuring does, and therefore you know you can't be orthogonal to the original state here, and have that would also be a problem. Yeah.
So the thing is, as far as I understood Andy's comment, it was essentially starting with what you have essentially all one state, so that's all state, right?
Yes, I mean it's you in a sense, like if you think of it as an initial state, it's kind of an empty state. I mean, it doesn't encode anything interesting, but technically speaking, we need to put something there because we cannot add qubits in a unitary. In the finite dimensional case. Okay, so let me state. There was another question.
So when you don't measure anything, is it like like this scatter and this cancel? So
yeah,
you're just looking at the same speed, right? But there is this phenomenon called quantum paradox.
Yes, but there you need to look at it in different angles. Like if you do the same, exactly same measurement on the same state without doing anything in between, and it's a projective measurement, like this one, like looking at one qubit, is it 0 or 1? That will always keep giving you the same result. The quantum Zener effect is something like, for example, I look at a state, like I ask, is it this one, like the 0? Then I ask, is it this slightly tilted state? and then slightly tilted, and I look at it over and over, and each measurement I do a little bit like this. And what you would intuitively expect is that if you start with a 0 state and you keep rotating your measurement each time asking, you have some probability, some reasonably high probability that one of these measurements will finally say, no, now you messed it up. I mean, the first one will probably still succeed because you're close, but at least in the end, when you're measuring something completely orthogonal, you will not succeed. Quantum Zener effect tells you that if you make these angles small enough that it goes, the probability 0 measurements will fail. So that's the quantum Zener effect. Or the other one would be if you have something that rotates slightly and you keep looking at it, it will stop the rotation, but that's just a different view at the same thing. That's the quantum Zener effect and doesn't help you. Okay, so let me state the theorem about that this works. So what the theorem says, if we ignore all the exact bounds and so on, it says if the probability that the original simulator succeeds is very close to a constant. For example, in our case, it was exactly 1/2, but you could pick another constant, at least as long as it's not 0 or 1. And let's say you are negligibly close to that constant, then the circuit that I described here succeeds with probability approximately for a reasonable number of repetitions. And the output is the same as for S, for the original simulator, up to some little error. I mean, if there's an approximate here, then there's an approximate here. But otherwise, yeah. So that is the theorem. And using that theorem, we now get, for example, a proof that graph isomorphism is zero knowledge, because we said we construct a simulator that guesses and produces the simulation if it guessed correctly. We plug it, we make it unitary, we plug it into this thing, and then Vatter's theorem says this gives us the same output as the original S. The original S produced a perfect simulation because the simulator with predicting what the simulator will say. Yes? Yeah, exactly. So if you would run infinitely often, get to one. I mean, if there's an equality here, then and you run infinitely often, then there will be an equality. I don't know whether you will. Maybe you can with negligible probability and get into a dead end from which you don't get out anymore in some imperfect case. I don't know. I mean, maybe not, but I can't guarantee that just from the statement of the theorem. Sorry? Yeah, but that's in the perfect case if there's an equality here. If you don't have an equality there, you may end up in then I don't know what happens. I mean, then I only know it approximately. No, or you make a bound, and then this is 1 minus something exponentially small. Yeah. So this would be how you would usually do it because you don't like exponential time simulators.
Just one question to clarify. So you say the probability of S succeeding needs to be approximately constant. Yeah. And this is, if I remember correctly, constant with respect to the input of S.
Yeah.
With respect to the auxiliary input of the.
Yeah, I will come to that in a moment. Yeah. So maybe I go to the next slide and tell something also about the limitations. So this oblivious rewinding lemma theorem by Vatter's works for many sigma protocols and similar situations, not just for graph isomorphism. But isomorphism is one example that is particularly easy to analyze. But there are some limitations. So maybe one that is surprising is this one. The probability that S succeeds needs to be approximately constant. So what does that actually mean? I mean, the way I wrote it here, it's just silly because this is numbers are always very close to a constant name themselves. So if I would write it precisely, it would be there is a constant strictly between 0 and 1 that for all auxiliary the auxiliary input, the probability of succeeding for that value of the input is close to the constant we chose. So the success needs to be independent of our auxiliary input. And that's actually, at the first glance, it's like, what does that mean? Do we even care? Well, at least in the graph isomorphism case, we don't, our simulated probability exactly one. The adversary cannot somehow try to be particularly nice to it and try to make it succeed more often, because our simulator, if it didn't make the right guess, it succeeds. Even the right answer would be completely obvious anyway. But you could have situations where maybe you have a simulator that wins with probability 1/2 for some auxiliary inputs and probability 3/4 for others. And Watcher's technique does not work there. So this is a interesting difference from the classical case. So the probability of S succeed greater equals some constant is not sufficient. And this can be annoying, for example, if I would take some extraction rewinding that we haven't looked at yet. But there where you get these two answers and get, but not with probability, you would want to rewinding to try again until you get the answer. Will not work with Watcher's rewinding because the extractor, the adversary can, depending on its auxiliary input, decide to be more or less nice to the extractor. So this is actually a relevant limitations, and I'm curious whether it can be avoided, but I'm not aware of any result that avoids it. Yeah, you had something.
Why can't you, for example, in the non-uniform cases, give success probability
Yeah, why can't I just give the success probability non-uniformly and then basically adjust the probability by just failing intentionally when I'm too high? The reason is that in the second loop of this, I will still have the auxiliary, the non-uniform information for the auxiliary, for the input I started with, but due to the disturbance here, I actually now have a different input that I continue with. So the auxiliary input that I have will then, in the second loop, already not be the right one. Yeah. Negligible probability is okay.
Okay, so
yeah.
If it's the reverse from the constant with negligible one,
yeah. That's
a negligible amount of cases.
You mean for a negligible fraction of the auxiliary inputs? But
yes, but the derivative is high, but it is high for.
I don't know.
We usually one of the worst is auxiliary. Right?
Yeah. But no, because if there would be a worst case auxiliary, it's not clear what I mean. Worst case is just the one where this trick that works the least. Exactly. So I think then we end up in some kind of cyclic dependency if we try to fix the trick depending on what the worst case is, because our fixed trick has a different worst case. Okay, but maybe I should continue because I also still wanted to go to the extraction rewinding, unless there's something really important of the first thing. But otherwise, I mean, I'm also after the talk, I can answer lots of questions. So let me talk about the full week, but not without interruptions. Okay, so let's go to the extraction rewinding. Let's remember first what was extraction rewinding. So there we had this setting that we have some algorithm, we give it a challenge, and we get a response. And then rewind, and then we get a different challenge, give a different challenge, give a different response. There's also the commitment in the very first message, but actually we can forget about that because it's kind of fixed. So we can, at least from the rewinding point of view, we can just imagine that our starting point is whatever state we are in after having sent the commitment. So for simplicity, forget about the commitment. That's not part of the rewinding. Just have this idea. We run someone with one input, get a response. We run again, get a different response. The first important observation is copying doesn't work because in the quantum case. Second important observation is that what oblivious rewinding technique, the one I showed you just before, doesn't work because it is oblivious. It applies the inverse of the simulator, and this uncomputes everything we've computed. And you cannot just like make a copy of part of the simulator state or output or something, because that breaks the proof. The proof uses the fact that we only measure whether it succeeded or not. If we try to learn something and keep it for later, we disturb the state too much, everything fails. So what was Oblivious Rewinding fails for this setting. I mean, it just doesn't apply. Yeah.
So just to try and understand what you said, in the measure state of the Oblivious measure state,
Yeah.
running a small part of the entire state.
I measure only whether it succeeded or failed.
Is that the same like a single qubit that's set to 0?
It doesn't matter whether it's encoded in a single qubit or whether it's something spread, as long as it's in that fact.
Okay,
I mean,
learn only a single bit, essentially.
and it's not that you learn only. It is important that it's that particular bit that corresponds to success or fail. Otherwise, I mean, if you would say, okay, try to learn, I just measure another bit instead, then at least the proof doesn't work anymore. I mean, there was this probability of it being approximately constant, which is specifically related to, so that bit, that specific bit that we measure needs to be the one that has a constant probability of being 1. Yeah. Okay, so what can we do? So again, as before, we can try to just do what comes into our mind and rewind by doing inverses. So I'm already here assuming that our algorithm, this cat here from which we want to extract, is unitary. So what we do is the following. We run the prover. This is boring. And now it's interesting. So now we run the prover, which is a unitary, with challenge 1. Technically, this means we have actually a lot of unitaries for each possible challenge. Unitary, so we apply the unitary that corresponds to challenge 1. And then we measure response 1. So now this thing so far is just a normal and will be valid with whatever probability the original prover has of succeeding. But that's the interesting part, because we need to go back and get a second interaction. So we use the same trick as before. We apply the inverse of the prover for challenge 1, because remember, the prover unitary depends on the challenge. And then we apply the prover unitary for challenge 2 and measure the response. And now the hope would be that not only the first interaction, so this com challenge 1 res 1 is valid, but also the second one, so the com challenge 2 response 2 is valid. And if there wouldn't be this measurement, then these two things would cancel out and we would just have commit, apply challenge 2, get the response. So basically the hope here is that this measurement of the response 1 does not disturb things too much. It will disturb something. Measurements always disturb unless they're boring. I mean, unless the outcome is deterministic. But maybe it doesn't disturb so that we gain something out of this. And we will see this is almost the case. So in general, this canonical extractor does not work. If I take a protocol, let's say the graph isomorphism protocol, and I measure here the isomorphism between the two graphs, I will get the this second interaction may not work anymore for some adversaries. But I can add yeah, that's what I was just saying. Yeah, so measuring the response 1 disturbs the state, and therefore this rewinding does not get us back to the original state, but to something potentially completely unrelated. But we can save the situation. Because one important fact to know about measurements is, at least as a rule of thumb, the more information we measure, the more we disturb the state. If we measure little information, we disturb the state a little. So let's have a little thought experiment. Let's say the response that we want to extract is only 1 bit. we have this measurement of the first response, and it disturbs the state only by a small amount. Then we undo, we go to something that is, I mean, it's not negligibly close to the initial state, but it's close enough that not everything completely breaks down. So we still have some non-negligible probability of getting the second response also, which is now also a single bit, and responses. That is encouraging, but it's not what we want, because the response is never 1 bit. If the response would be 1 bit, we could also have just guessed it and extracted from our guesses without talking to anyone. So responses are always something long and not guessable. So it seems this approach does not really work, but it turns out the idea works. So what we want, because the measurement does not care how many bits we measure, like how many output bits we have, like how long the string is that describes the measurement output. The quantum information theory only cares about how much information theoretically did I learn. The fact that the extractor finds this response highly surprising does not mean that maybe information theoretically this response is completely known, except you would have to run exponential time. And this is some extra assumption we can add to the protocol. So if we have the property that for any challenge, for any challenge and commitment, there exists at most 1 valid response, then measuring the whole response effectively just measures, is it valid or invalid? And if it's valid, I can measure the whole one because that is no additional information that I've gotten because there exists only one. I may not know it, but information theoretically it's already there. So if the response is determined by the challenge, then measuring the response completely leads to the same amount of disturbance as measuring only 1 bit. For measuring only 1 bit, we can make some bounds and figure out how much the disturbance is. And I don't want to go through the calculations, but the basic answer is if you have a success probability that 1 run succeeds, then the probability that the 2 runs with the rewinding succeed is p to the 3. Roughly. It's p squared. So we have a difference there. So we get a p to the 3 chance of succeeding. I say roughly because there's a small probability you need to subtract that your 2 random challenges are actually the same challenge. If there are a lot of challenges, this will be negligible. If there are only 2, as in our example, then this plays strongly into it. But in any case, it will work. You will get 2 valid interactions with a probability that is sufficiently high to make all the definitions of proof of knowledge happy. You get the 2 interactions, and because of the special soundness, you can extract your 2 interaction, your witness. But we have added this 1 extra condition, the strict soundness. And the strict soundness is unfortunately a strong condition. Because strict soundness means there can be only 1 response. And now let's look at graph isomorphism. Yes. No, because it is completely unknown to us, but it's information theoretically already there. Same as the witness. I mean, it could be that the witness has actually only has 0 bits information if it's uniquely determined by the statement, for example. So that would be something that could happen. Or, I mean, if the language is, we decide is polynomial time, the witness could actually have 0 bits as well, or whatever. So it's very important to distinguish here between the representation complexity of the witness, like how long is it to write down, the computational information in the sense, like, I mean, can I guess this thing when I'm stupidly polynomial time or not? And the actual information theoretical complexity, which can be very low. And in this case, it will be very low by assumption of the strict soundness. No, it doesn't mean that. I can make counterexamples to that, but it just means for every challenge there is only one answer. I mean, this could be achieved, for example, by committing to all your answers. Yeah, which does not involve witnesses at all. Let me talk about the graph isomorphism. So the response here would be that one. Is it, well, between two graphs, you can have more than one isomorphism. So this protocol actually doesn't fall into that setting. And we don't know, unless I have missed the paper that studied this, we don't know if this is a quantum proof of knowledge. However, what we do know, if we restrict ourselves to so-called rigid graphs, so rigid graphs are graphs that have only a trivial automorphism, then there can be only one isomorphism between G and H, and then it has strict soundness. So that would be an example, not a very nice one, because as far as I know, deciding rigidity is a hard problem too. So, but I mean, maybe you could have it as a promise problem or whatever. Also, yeah, I don't know. It's not even in NP, I think. Yeah. So yeah, trying. Yep. Okay, I'm saying this protocol is, we don't know. I'm not saying we don't know secure protocols, but this protocol is, it has no computational assumptions. As soon as I put commitments in, I will have a computational assumption either in the ZK or in the proof of knowledge property. So we don't know an information theoretical graph isomorphism quantum proof of knowledge, zero knowledge thing. So that's one example. So you end up having extra assumptions. So yeah, this is what I was just saying. It's proof of knowledge only if the isomorphism is unique. Otherwise, it's an open problem.
Sorry, I think it's a stupid question, but like, doesn't that make that point though? Like, for example, my error is supposed to get a jump. Based on the possible challenges that I can get, I commit to my responses for all.
Yeah. Yeah, it does work. It's just not information theoretically secure anymore because your commitments will either be will not be information theoretically hiding and binding at the same time. So that's basically the problem here. So because I mean we do know zero knowledge proofs of knowledge in the quantum setting for all of NP. Basically roughly with the techniques from here, but only under computational assumptions. So one way what you could do is you can put in a commitment that is perfectly binding. Why do we need the perfectly binding? Because we need that information theoretical, the response determined. So if I have a computationally binding commitment computationally, then we have the problem that that still doesn't determine information theoretically what the measurement will reveal. So it needs to be perfectly binding. We can weaken that. We can use something that is called collapse binding. I mean, here's the paper cited, but I don't want to go into these definitions because that's, well, because we don't have time. But I mean, we can weaken that, but we cannot do it under the same assumptions as classically, because remember, we had these explicit counterexamples where everything goes. So these are the, here they come back to hunt us. So basically the message with rewinding is you always need to remember it's harder, you need to be more careful, you may get extra conditions, but a lot of things work when you have this idea. Rewinding means just applying the inverse. Yeah, and this horse race, just to get it into the picture again, also can be done with this kind of rewinding, but you cannot do it. Collision resistance doesn't help because collision resistance does not give you that there is only one answer. So you also need this well, an injective function would mean that you can really do it directly with the tricks I showed you. You can weaken it to something called collapsing, which I didn't cover. Yeah. So there's more to rewinding. So you can, there's, for example, in Katrin's talk, this measure rewind measure was mentioned, which uses rewinding, which, I mean, I'm not very familiar with that, but I think it's in a way that is distinct from the two cases that I described here. But I think it's specific to the proof of this O2H theorem. Then there's Fiat Charmier, where to do rewinding and you want to have, then you panic. Well, that was at least when I was working on my first paper on Fiat Charmier. By now we are not panicking anymore. We have tricks for it, but that was a tricky one. And there's no general answer how you transfer rewinding from the classical case to the quantum case. And that's basically what I wanted to tell you, except I also wanted to mention that there are postdoc and PhD positions available. So little advertisement here, broadcasted on the internet, put on YouTube, yay, for free. Okay, so that's the talk. I'm 5 minutes over time. Thank you for your attention.